Yesterday we began talking about polyprotic acids and monoprotic acids. Today we want to continue that thought. Yesterday we said that sulfuric acid ionizes in two stages. Let's look at that in a little more detail. In its first ionization, sulfuric acid is a strong acid, which means that nearly 100% of the original molecule will ionize to release one of its hydrogens. And in the process of this, the hydrogen sulfate will be completely changed from H2SO4 to just HSO4 negative. It has lost one of its hydrogens, and the hydrogen didn't take its electron with it and left it with the remaining polyatomic ion, and so it is negatively charged. So this is kind of what it looks like. We have H2SO4, that's the original molecule, and it ionizes in a water solution, and that hydrogen will be hydrated with water to form H3O+, that's the hydronium ion, and what remains is a polyatomic ion called hydrogen sulfate. In the second stage, in its second ionization, hydrogen sulfate ion is a weak acid, which means it won't ionize very well. The first stage it ionized very well. This stage won't ionize nearly as well, and it's going to establish, it says, the following equilibrium. We kind of talked about that yesterday. So we'll start out with the hydrogen sulfate ion right here, and what this hydrogen is going to be removed during ionization. It's going to join up with water to form the hydronium ion, and what will be left behind will be just the HSO4 and one extra electron. So now it's sulfate ion. But what you can see happening here is that it says that it will establish an equilibrium. These two arrows pointing in opposite directions tell us that this reaction will never completely finish. At the very beginning, there won't be very many SO4 2 negatives, sulfate ions, and as it begins to ionize, that concentration will begin to increase, and this sulfate ion will find hydronium ions to attach to and reform the original HSO4, the original hydrogen sulfate ion. And but at the very beginning of this process, there will be more of these than these, and eventually at some point the number of these being converted to this and the number of those being converted back to this will establish some equilibrium, some place where it's going back and forth at the same rate. Now, all stages of ionization of a polyprotic acid occur in the same solution. You don't have to take one out and put it in another one. They all happen in the same solution. And sulfuric acid solutions, because of the two stages that we've talked about, we're going to have two stages. In both stages, we have hydronium ions that are forming. In the first stage, we had this forming. And in the second stage, we had this forming. So in the same solution, we're going to have sulfuric acid molecules, hydronium ion, hydrogen sulfate ions, and sulfate ions, all in the same solution. So sulfuric acid is the type of polyprotic acid that can donate 2 protons per molecule, and is therefore we call it a diprotic acid, kind of like we talked about yesterday. Phosphoric acid is a type of polyprotic acid known as a triprotic acid. which because it has 3 hydrogens per molecule, and so it's able to donate 3 protons per molecule. So this would represent the first stage, where we have hydrogen phosphate ionizing in water to form a hydronium ion and a H2PO4 negative ion. But notice that in the very first stage, there is an equilibrium formed. Not all of these will be converted into all of these, as it was for sulfuric acid. So this very first stage is already not going to go to completion, but there will be some of these ions in solution along with the hydronium ions, and some of these still that haven't ionized. In the second stage, this particular ion right here, H2PO4 negative 1, is going to ionize and form some more hydronium ions, and then it's going to convert to this hydrogen phosphate polyatomic ion. But again, it's in a equilibrium, so that means not all of these will be converted into all of these. Along the way, as this number increases, there'll be more of those combining with hydronium ions to form this particular ion. Then in the final phase, there will be a few of these that we have over here again that can ionize in the third stage to form a few more hydronium ions, and finally leaving a phosphate ion at the very end. But again, this is an equilibrium will be established eventually, because some of these will combine to form this. And so in this particular solution, we're going to have all of those particular ions present at one time. So as with most polyprotic acids, the concentration of the ions formed in the first ionization is going to be the greatest. So, and then there will be lesser concentrations of the respective ions from each succeeding ionization. So here's the oxyacids of chlorine. Each of those have only one hydrogen, so we would call those monoprotic. And how well they ionize increases toward the right, and also how acid it becomes. In other words, the amount of hydronium ions formed will also increase toward the right. So the one at the right will go to completion when ionized. The one on the left will establish some kind of equilibrium. Okay, now it's time to introduce a third theory of acids and bases. Each time the theory or definition changed was because they found some substances that behaved like acids and bases but didn't fit the original definitions. So each time we had to kind of like broaden the definition. And the Lewis definition of acids and bases deals with electron pairs, not protons or not hydrogens. So it deals with electron pairs. The Arrhenius and Bronsted-Lowry definitions assume that the acid contains or produces hydrogen ions. So both of those had hydrogen ions. Arrhenius called them hydrogen ions, but Bronsted referred to them as protons, but they are the same thing. This third acid classification is based on the bonding, and the structure includes as acid substances that don't contain hydrogen at all. So now we can have some substance that actually behave like an acid, but it doesn't have any hydrogens. So Lewis's definition emphasizes the role of electron pairs, and if you notice that in our discussion we talked about some substances having electron pairs that the hydrogen could attach to. So that this one just focuses on that idea instead. So a Lewis acid is going to be an atom, an ion, or a molecule that accepts an electron pair to form a covalent bond. And this definition is the broadest of all three. It includes more kinds of substances that behave like acids than the others. In fact, Arrhenius is probably the narrowest. Next would become the Bronsted-Lowry, and then Lewis is the broadest. And it applies to any species of ion, atom, or molecule that can accept an electron pair to form a covalent bond. That's an important word there, covalent bond. They're going to share the electron pair with this other species. And if we take what we have looked at before when we were talking about HCl dissolving in ammonia, well, it was the hydrogen that was donated by the HCl, so we're going to focus on this part right here. This hydrogen ion came and attached itself to this electron pair. And so we see it attached to the NH3 over here. And then we more commonly write it as NH4, ammonium ion. So you can see, well, let's go back. You can see in this that this hydrogen over here on the left, this hydrogen ion or proton accepted ammonia's electron pair. So we said a Lewis acid accepts an electron pair, so this hydrogen is acting like an acid according to Lewis's definition of an acid. Now, they've also found that even silver ions can be a Lewis acid, accepting electrons pairs from ammonia to form a covalent bond. For instance, if we have a silver compound and we put it into ammonia, and the 2 up front right here tells us it's going to take 2 ammonia molecules, and it's going to attach 2 silvers to it. I mean, no, take that back. It's going to take a silver and attach 2 ammonias to it. Now this one's just ammonia written backwards. Actually, in reality, it's written in the correct form, but we're so used to writing it this way that if I wrote it like this, you would say I wrote it backwards. But that's actually the right, according to the way we're supposed to write things, with the positive first and the negative second, but that's neither here nor there. So silver, and so silver is accepting the electron pair, and so it's going to form this complex polyatomic ion that has a positive charge. It's a silver attached to 2 ammonia molecules. So any compound in which the central atom has 3 valence electrons and forms 3 covalent bonds can act or can react as a Lewis acid. So it does so by accepting a pair of electrons to form a 4th covalent bond. Remember, we need to have 8 around the outside, and that way it completes its electron octet. So here is an example of a substance that we talked about before. This is boron trifluoride, and we know that this was a trigonal planar molecule, if you remember from that discussion from way back when. And an extra fluorine is going to be attached to it in this place right here. This fluoride, I should say, not fluorine, fluoride has an extra electron from being attached to some other positive ion, and it's going to bring its electron pair right here over, so boron will now have 8 around its central atom. So this substance over here accepted fluoride's electron pair, and in the process forms this negative polyatomic anion. So here's how we would write this, the Lewis structure in the form of a regular formula, and it forms this new ion, negative ion. So in this situation right here, it was the boron trifluoride that actually accepted the electron pair, and so it's what's acting as the acid. So the Lewis definition of acids can apply to species in any phase. So we've talked here about in water, but in solution, but it says in any phase, gases or liquids or solids. Now a Lewis base then is, if you kind of notice the pattern, it's going to have to be the opposite. A Lewis base is an atom, an ion, or a molecule that donates an electron pair to form a covalent bond. It's going to donate an electron pair. An anion is a Lewis base in a reaction in which it forms a covalent bond by donating an electron pair. So fluoride in the previous example was the one donating the electron pair, so the fluoride ion acted as a Lewis base. So in every situation you've noticed so far, if one substance is acting like the acid under that definition, there's got to be another substance that it's combining with that's behaving like the base. So the fluoride ion right here in the center is the one that's acting like the Lewis base. This was the part that accepted the electron pair, so this was it was functioning like an acid. So notice in this situation right here with the Lewis acid-base definition, there are no hydrogen ions, there are no hydroxide ions at all involved here, but we have substances that are behaving like acids and bases. So a Lewis acid-base reaction is the formation of one or more covalent bonds, that's kind of maybe an important thing to remember, between an electron pair donor and an electron pair acceptor. So let's compare these three different definitions. In Arrhenius, it was an acid if it produced a hydrogen ion, or which combines with water, because Arrhenius said it had to happen in water, and formed a hydronium ion. It produced those, so an acid was something that produced those, or was releasing those, and a base was something that produces hydroxide ions. In a Bronsted-Lowry definition, an acid was a proton donor. So kind of similar here. And in a base, it's a proton acceptor. So proton donor, proton acceptor. Now in a Lewis, since it's not talking about protons, it's dealing with electron pair, kind of an opposite. An acid is an electron pair acceptor. Notice these are opposite. And a base is an electron pair donor. Again, notice that these are opposite. So a proton donor is also an electron pair acceptor by the two different definitions. and a proton acceptor is also an electron pair donor. And that's the end of this section.